Okay, so let me first have a brief introduction. Okay, so hello everyone. So welcome to our this week rigorous efficient seminar talk, and also this is the last talk for this semester. And today we're very glad to have the Professor Bahar Asgari to give us this talk about the uh, machine learning from sparse patterns to smart acceleration machine learning method for the future of computing. And Bahar is currently assistant professor in the Department of Computer Science at the University of Maryland, and with a joint appointment at UMIACS and EC department, and also affiliation with the Artificial Intelligence Interdisciplinary Institute at Maryland. And before joining the UMD, she spent a year on the Google System and the Service Infra team, and he focused on improving the performance of the Google systems. And she earned her PhD from the Georgia Tech, and Baha is a recipient of the very prestigious the DOE Early Career Award, and also received the Teaching Excellent Award in the Maryland. And she was also selected as a rising star in EECS in 2019. And her research group at Maryland, the Computer Architecture and System Lab, is dedicated to shaping the future of the computing and the primary goal of the enabling intelligent, dynamically reconfigurable architectures. So that is a very, very important research topic. And so I remember for this year, Mike, I remember there's one session that I think most of the paper are from your groups. It's so amazing, very impressive. Yeah.
Thank you so much. Yeah.
Okay. Okay, so right now, Bahar, so it's your turn. Okay.
Sure. Yeah. Thank you so much for a very kind introduction. Yeah, I'm very excited to talk a little bit about the research that we are doing in my research group, Castle. So to start with, because actually it was the last sentence of the kind introduction as well, I wanted you all to just for a second think about how the future of computing will look like. So I guess we are thinking about like really different kind of things that will happen in the future of computing. Some of you may be thinking about some new technology like quantum computing, some like maybe more GPUs, huge data centers, or maybe tiny like small devices, edge devices. But one trend that I'm sure that all of us have noticed is that there are so many recent accelerators, domain-specific accelerators or DSA. We see so many papers from academia, but it's not just at research level. We already see that there are much like investments from industry as well. There are several startup companies that started to design their own hardware, mainly accelerators for machine learning. But of course, some of them have been running like HPC workloads, such as Sparse and SambaNova. And also, you all know that even big companies that were historically, not all of these companies are historically designed for just for like software side, but for instance, Google have been also designing their own domain-specific architectures, TPU, and then they are even deploying them at large scale recently. So maybe domain-specific architectures are going to continue to create the future of computing, not maybe for like 10 years, but at least we know that for the next few years, we are going to face so many domain-specific accelerators. But the question I wanted to ask, basically try to find answer for, is that are these domain-specific architectures or DSAs efficient and effective, and can they be the future of computing? So to try to think about that, we of course want to see if why they may not be efficient and effective. So for that, let's go back to actually a non-DSA systems that we have today that are very powerful. So today let's take a look at two powerful, the fastest supercomputers that we have in the world. One, El Captain from LLNL, and the other one, Fugaku in Japan. So these are supercomputers. They use CPUs and GPUs. And then, as you can see, when they are ranked, when they are running LIMPACK, which is a dense benchmark, they can achieve and they can work closer to their peak throughput, which is good. This is why we design the hardware, why we design a system. We want to achieve its peak performance. But as you can see, when they are running a sparse benchmark, they just achieve a tiny fraction of their peak throughput, which is like 0.62% or 2.9% for Fugaku. Why I'm showing these? So these are not using domain-specific architectures. But if we want to have efficient systems for the future, we don't want domain-specific architectures to face the exact same issue. However, I'm going to talk about it. We see that not all we may face the same issue if we won't be careful about sparsity. So first thing first, sparsity dominates. Sparsity is not just about that one benchmark. All the data around us is sparse. So sparsity dominates, and then we must design for sparsity. And then that's what we do, as we are going to learn more about that today. But sparsity is everywhere. Why we even care about sparsity? Let me give you some examples. Even if you haven't noticed, I'm sure that at least you have worked with one workload that is sparse. For instance, DLRMs or deep learning recommendation models that you use every day to see what movie to watch, what music to listen to, what product to purchase. Pattern of accesses in them is sparse. In scientific computing, traditionally data is sparse. You know that LLMs, DNN, we started with like DNNs to make them kind of smaller, but recently with LLMs, we know that they are huge. You have to use methods such as pruning to make them smaller. So even though they may not be naturally sparse, but we make them sparse. So in LLMs and DNNs, we also have a sparsity. And then in some other domains, such as graphic analytics, not all the nodes are connected. So data there is sparse too. So it doesn't just prove that sparsity dominates, but it also shows that sparsity is different. Workloads are different. And going back to the fact that we see so many domain-specific architectures, so this diversity causes some challenges. For instance, in this table, what we see is we see the workload distribution based on Google's TPU version 4 paper in published in 23. As you can see, the distribution of different workloads that Google runs varies a lot in years. So if, for instance, Google were to design some domain-specific architectures in 2016 for just RNNs, as you can see, they no longer in 22 are the dominant workloads. So this is just one example, but the point is that we cannot just design for one very specific workloads and one very specific data. Programs are diverse. We have to design for diversity. So this is the two key theme of my talk today. Sparsity dominates. We need to design for the sparsity, and programs are diverse. We have to design for diversity. So I want to try to find answers and solutions for three key research questions about this, how we design for diverse sparsity. The main the bigger part of my talk is going to focus on the second question, but I'm going to start by giving you one example briefly on how to design for sparsity to give you a sense. For instance, what needs to be optimized. Then I'm going to talk about how to make decisions based on sparsity, based on diverse sparsity, which is going to help us get connected with using machine learning methods. And then if time allows, I'm going to give you another example on where in domain-specific architectures, of course, a sparsity-aware decision can help. So let's just start with the first part and how to, in what cases and how we can design for sparsity. So as I mentioned, the sparsity became very important even recently because of LLMs. So the first work that I'm going to talk about, which is a Micro 25 paper, is about optimizing for basically sparsity for LLMs. And then I want to I don't have time to go over like all the papers, but I wanted to also refer you to Dongyal's Nurip's paper, which is about the work that I'm going to talk about, but it is also about sparsity, but for KV caching, as you know, it's super important. So please feel free to take a look. So going back to sparsity in LLMs. So as you know, the big challenge is that LLMs are huge and they are getting like massive and even bigger every day. So we have to think about efficient ways to handle data, whether it's storing them, moving data, how to cache it, and all those kind of things that all of them are challenges because of size of the data and memory footprint. So the traditional method of pruning can help us to get rid of data that we don't need. And that it can in theory, help us reduce the memory footprint by 30 to 70%. But if we really want to be effectively get rid of data that we really don't need, we have to go with unstructured pruning so that we can also preserve like accuracy and then also more effectively basically reduce memory footprint. What is the challenge? Why can't we do that? So one challenge here is that the current hardware, in particular GPUs that we use every day for running LLMs, cannot exploit unstructured sparsity. So GPUs only support structured sparsity. Why? Because of the structure of basically their microarchitecture, the architecture of tensor cores. So they dictate or force pruning methods that adapt to this, to their kind of type of the computations that they have. So if we were to prune data, in particular like LLMs based on structured sparsity, we lose the opportunity. And one main drawback is that there would be significant accuracy drop. So let's say that we want to go with unstructured sparsity. We want to prune with whatever we want. I'm going to show you how, but there is another problem with that. The other kind of challenge is that now if we prune data, if we have that unstructured sparsity that we are looking for, but then how to save it? So when data is sparse, we often usually basically compress that. There are some traditional compression methods. I'm sure many of you have heard of them, used them. For instance, CSR, shown in blue in this diagram, COO or coordinate, which just says the coordinates, shown in orange. And we can also use some recently proposed methods. For instance, the one in Flash LLM. My apologies, I forgot to add the Flash LLM's footnote here. It's a recent great work. So the existing sparse formats or compression formats are not efficient for the level of sparsity that we are looking for to reach with unstructured sparsity based on compression ratio, with the formula which is compressed size over original size. So what we propose, as I mentioned, Croissant has three components. We start by making a decision of which compression format we need to use. So the green line here is the compression format that we have proposed that I'm going to talk about next in the next slide. So what is Croissant's compression format? So it simply uses a bitmap-based representation because we tried it and saw, based on the previous diagram, that it is efficient in terms of compression ratio. How does it work? It is a simple bitmap-based representation in which you would save the non-zero values and then a bitmap in which the exact location of ones are going to represent the locations of the values of non-zero values. So it is going to be efficient for 30 to 70% range. And then we are basically applying the bitmaps in a tile format to facilitate the processing on GPUs as well. But so far so good. We can go with unstructured pruning. We know what compression format to use. But what else can be co-designed? What else can be co-designed with that format? How we can guarantee that we can also process data faster, not just saving data and then moving data around more efficiently. So we don't want, although my job is to design better hardware, more efficient hardware, but we never jump to the decision that, okay, let's go and change the hardware. We want to try to optimize for whatever hardware resources that we have. In this case, it's GPUs. So first, we try to optimize GPU kernels so that it can run the bitmap-based LLMs faster. You can refer to the paper. It's a very dense paper. You can see the details of how we exactly optimize for that. But the bottom line is that if you are using this tile-based bitmap format, you have to be aware of what type of tiling you use, mainly to avoid bank conflicts. And then for that, we are using column-wise tiling. So that's the GPU kernel that we have, a GPU kernel that's customized for bitmap format. Now, is that enough? Can we do better? Yes, we can do better. I'm going to show the speed up number. It is fine. We can just go with the GPU kernel, still run on GPUs. But can we just change the hardware architecture of GPUs just a little bit to gain huge speed ups? Yes, we can. So basically, the third component and last component of Croissant is that we change the sparse tensor core, basically tensor cores of GPUs, to make them work directly on the compressed format. You can find the details of these numbers, steps of this hardware that you propose for that. Simply saying, it avoids basically a step of decompression, because when you have data in a bitmap format, you know that you can design a customized hardware for just processing data directly. So that is simply what we do for that processing, and then the hardware that we are adding to the GPUs is also minimal, as I'm going to show in the numbers. So the bottom line is that the speed ups that we achieve. So if you just go with the software, basically non-hardware optimizations, if you just want to run on GPUs, you can achieve like 2 times or 1.4 times the speed up, depending on what you're comparing to the state-of-the-art work or available libraries. And if you add the tensor core optimizations as well, you can achieve up to 2.75 times the speed up. And then you can find some numbers about what is the actual token per second in our paper for different batch sizes for different models. So for instance, by just using software kernel, you can achieve 135 token per second. And then if you, again, want to optimize it further by also deploying this Sparse tensor core, your throughput is going to get to 2.6 tokens per second and then these results are for Llama 2, 7 billion and 13 billion. And before I move to the second question, I want to emphasize again that this work is not just about performance. Remember that I started by talking about memory footprint, and that if you can reduce memory footprint, it has different benefits. One, of course, is that if you have a smaller size of data, you can also now fit more, you would have more space to fit other things that you need, for instance, KV cache. And also when you have a smaller data, you're going to move less data. And then remember that these days, energy is dominated by moving data and accessing data, and then it's super important to reduce the two. And of course, we don't want to achieve all of these by, again, costly hardware. So the minimal decoder hardware that we propose to add on top of GPU's architecture is just 0.018% of the total GPU area. So that was just one example how we can design for sparsity. But remember that I told you that sparsity is diverse. We don't want to just spend our time designing for one particular type of sparsity, for instance, LLMs. So the question is how to make decisions based on diverse sparsity, or in other words, where in running workloads diversity, we need to be aware of diversity of sparsity. So I'm going to give you two examples here. One is that if we have let's say that we design a sparse accelerator, how we can efficiently use it, how we can make the sparsity aware decisions. And then if we were to change the hardware as well by making some decisions based on sparsity, how we can do that. So first thing first, let's talk about the work boosting the efficiency of current sparse accelerators using spectral clustering. This work is also a Micro 25 paper led by my second-year PhD student Sanjali Yadav. So this work is going to be about sparse accelerators that usually accelerate sparse matrix to sparse matrix multiplication because that's the main kernel in several application domains that I have named in this slide. So just to give you a little bit like background in case you're not familiar with sparse SPGEM accelerators, so they usually use one of the three different data flows or algorithms for matrix-matrix multiplication. One is taking rows from the first matrix and multiplying it with columns of the second one, inner product. The other one is taking columns from the first one, rows from the second matrix, which is called outer product. And then in the last one, I'm going to give you a little bit more details on those. And then last one takes rows from the first and second one, and it's called row-wise product. So basically, all of them are doing matrix multiplication. Functionality-wise, they're all the same. Their differences is about in what order we are performing multiplications and in what order we are aggregating partial products. Because of that, they have some pros and cons. So for instance, if you use inner product, so first thing first, because you are accessing the two operands in different manner, in different like row-wise or column-wise, they use different compression formats. It is a drawback. We don't want to do that. Again, for more details, you can refer to our paper or other papers that talk about the same issue. So most importantly, inner product requires index matching, index intersection, because you don't want to multiply value on non-zero values with zero values. You have to find the locations of non-zero values to multiply them. It incurs overfetching because of repeated accesses to B. That's not optimized if you use inner product, but it also has some advantages. Of course, it's not just about drawbacks. It maintains manageable partial sum granularity because basically it is the order is dictated by producing the outputs in order, and it enables efficient output reuse. So outer product also suffers from the same challenge of using different compression formats because we are taking columns from the first one, rows from the second one. So one benefit is that it does not require index matching. Again, if you think about that, it is you can realize why, but basically because you are taking all the non-zero values and then you can't just simply multiply with all the non-zero values in the row that you take. And then it achieves good input reuse of B because while you have B, you can also multiply that with like all the non-zero values in A, but it has its own drawbacks. So it incurs large volumes of partial sums because you are basically randomly generating partial products of any that corresponds to any values in the output. And basically, in other words, it exhibits poor output reuse. We want both output reuse and input reuse. So there is this third data flow that, in my opinion, most efficient one. And then there are papers in all three data flows, but more recently, we see more papers that use the row-wise product because it has several like advantages. For instance, it uses the same compression format because we take rows from the both matrices. It does not require index intersection because, again, you need to take just non-zero values and multiply them with all the non-zero values from the rows from B that you take. Now, it has one disadvantage. It exhibits poor input reuse. This is going to be the focus of the next slide, so I'm going to get back to that. Drawback, But I mean, anything else is positive about it. It maintains manageable partial sum granularity, although not as good as inner product, and it achieves good output reuse. So it seems that if we can make row-wise product-based accelerators efficient for diverse sparsity, we can basically get into an efficient sparse accelerators because everything else is efficient already about row-wise product. So let's focus on that particular drawback and see what we can do about it. So if you focus on this matrix multiplication and then the non-zero values of matrix A, so let's say that I take this row, based on the location of the column indices of that row, you are going to fetch the rows of B. For instance, these that are shown in this slide. Now, the problem is that, as you can see, in the two highlighted rows that we have here, the two of them are using basically the same, they have common column indices, meaning that they need same data from B. However, if your matrix is huge, by the time that you get to execute that third row of A, the values of B may no longer exist in your cache, of course, if you have a cache. So that is why you may not fully utilize or optimize for the input reuse of B. That's why I mentioned that's a challenge. So of course, I guess if you think about it, you say that, okay, it seems that the solution for that is obvious. We can just reorder the rows of A. For instance, why don't you move or basically process those two rows one after the other so that you can improve the reuse of matrix B. So I agree. Why not? We can do that and prior work do that. But the thing is that remember that sparsity is diverse and we cannot easily do that. So the reordering is not easy. So although prior work proposed reordering mechanisms, it is often suboptimal, failing to maximize the potential reduction in memory traffic. Besides, the pre-processing steps are also typically slow and inefficient and making the cost of reordering unjustifiable, even when performed for just one time. So it's going to take a really long time. So why do you want to even reorder? And finally, like certain sparse patterns even do not benefit from reordering, but you may think that it is. You reorder, and in the end, you realize that you don't. And all of these are happening because of diversity of sparsity. It is not obvious. So existing studies lack a mechanism to identify such scenarios where the optimal strategy would be to avoid the reordering altogether. So in this paper, we propose a new row reordering technique that leverages spectral clustering to minimize memory traffic and improve data locality. Additionally, BOTIS, which is the name of this work, it trains the decision tree model to predict whether row reordering will yield sufficient performance gain to justify the associated overheads. And we integrate BOTIS with state-of-the-art accelerators to demonstrate its efficiency in reducing memory traffic and data movement. As I mentioned, they are very important on various configurations. So the essence of this approach, the essence of BOTIS is that no additional architectural components are required to integrate it with state-of-the-art accelerators. Instead, we introduce a broadly applicable preprocessing mechanisms for any accelerators supporting row-wise matrix multiplication. So we are kind of enabling, making sure that when sparsity is diverse, the current sparse accelerators are working at their peak potential. So as I mentioned, a key insight of BOTIS is using spectral clustering, which is particularly effective for non-linearly separable or irregular shaped data. You might be familiar with spectral clustering, but not for this problem. So I'm going to explain how we can use it here. So basically, unlike k-means, which relies on linear boundaries, spectral clustering captures complex patterns by embedding data into a new space using eigenvector decomposition, which I'm going to briefly talk about in the next slide. So let's take a quick look at steps of using spectral clustering in booties. So given a matrix A, we first calculate a similarity matrix by computing the dot product of the matrix with its own transpose. You're going to see why. So since the matrix is in binary format, basically non-zeros are replaced by one. So that's the matrix of A we take to calculate similarity matrix. The similarity matrix basically effectively captures the number of shared column coordinates between the two rows. Remember that that is the thing that we care about, shared column coordinates. So in fact, each entry in the similarity matrix shows how many columns the two rows have in common. For instance, you see that the two highlighted rows here don't have any shared column index or column coordinate. Therefore, the value is 0. And then for these two, they have one shared column coordinate. Therefore, the value is 1. So the next step, based on the similarity matrix, we calculate the Laplacian matrix. It basically transforms the similarity matrix to capture both the local and global structure of data. We are using spectral clustering to, in a better way, easily find out that structure of sparsity. So for more details on all these steps and algorithms, pseudocodes, please refer to the paper. I want to just quickly give you a sense of like what the steps are, but of course you can find more details in the paper. So after that, we need to calculate the eigenvectors of the Laplacian matrix. So we extract top k eigenvector of the Laplacian matrix. The top k eigenvectors capture the most meaningful cluster structure by minimizing noise and focusing on a stable relationship across rows. Again, that's what we care about. So in this spectral space, the rows of the original matrix are better separated, even if they were non-linearly separable in the original space. So now what we do, we restrict the top k eigenvector to power of 2 between 2 and 32 because eigenvector calculations can be quite expensive, and our experiments show that this range is sufficient to cover the diverse sparse focus that we use. But I mean, of course, other ranges can be used. And then the image here in this slide show how clustering can impact the output for different k values. The most ideal case here is k equal to 2, where I hope that you can visually see the column coordinates are aligned in straight lines when k is equal to 2. So after rows are transformed into the spectral embedding space, K-means leverages these coordinates to partition the data, ensuring that even rows with complex nonlinear patterns in the basically original space are grouped into coherent clusters in the spectral space. So basically, it's simply saying if two rows have very similar values across all the eigenvectors, they may belong to the same cluster. So for this particular graph, we set k equal to 2, since, as I mentioned, for that specific input matrix, we observed that k equal to 2 was the most optimal one. And then you can think of eigenvectors as non-zero patterns, the patterns of non-zeros that run across the rows. So one eigenvector, for instance, eigenvector 0 is one type of pattern. Eigenvector 1 is another type of pattern. And every row gets a score for eigenvector 0 and for eigenvector 1. And in the graph, each row is plotted using the two scores as x and y coordinates. And basically rows with similar scores on both patterns, eigenvector 0 and eigenvector 1, would land near each other. That they would be in the same cluster. So that was, I mean, too much details. The bottom line is that, so if you use spectral clustering, you can more easily find the patterns, and getting back to the problem that we try to solve, we can easily um, more efficiently use current row-wise product sparse accelerators for diverse sparsity. Um, but what is this key insight is not limited to that. We also have an adaptive decision making. So another basically critical component of BOTs is the decision tree model, which determines first whether matrix reordering should be applied, and if so, it selects the optimal K value for spectral clustering. So since the spectral clustering is highly sensitive to parameter tuning, particularly to the choice of K, as we just saw, it is essential to develop a systematic approach for parameter selection that generates, basically that generalizes across matrix structures. And then based on the feature set, which represents the sparsity of the matrix, it predicts if the reordering should be applied. And if so, then we run another model which predicts out of the possible like K values, which K values should be selected. So the features we use in like the training includes features. We want to basically represent sparsity of the matrix in a form of like features. So they could be some global sparsity, like the ratio of non-zero values to the total elements, the variance of non-zeros per row, per column, which captures basically the how uniformly the non-zero values are distributed. For data sets, we use matrices from Sweet Sparse, and we collect performance metrics such as memory traffic and execution time, and the K value that yields the best trade-off between these metrics was recorded as the optimal choice, basically for that value. We have integrated BOTs with, so as I mentioned, BOTs is not like a new accelerator. We have integrated it with 3 prior row-wise based accelerators and simulated them using trapezoid simulator. So each of these accelerators have different cache sizes. They have different like configuration, number of PEs, size of on-chip SRAM is different. So we want to do this to illustrate that our reordering algorithm and our decision tree model can be adapted to different underlying hardware, different configurations. And our baselines for comparison includes 3 prior reordering algorithms. So we are applying on top of some of the accelerators, and we are comparing with the reordering algorithms. So we analyze each of the prior algorithms and their downsides and common pitfalls in the paper in more details as well. So you can also take a look. But in short, if I want to give you a one-line summary, most of them are greedy algorithms that may get stuck in suboptimal loops. So basically, I want to note that the 2 gammas, one all in upper cases and one not. One of them is Gamma's accelerator, the other one is Gamma's algorithm. It is not a typo. So let me just show you a couple of results before I move to another word that I definitely want to talk about. So let's take a look at the pre-processing time, first thing first, or the time to run the reordering algorithm, the spectral clustering algorithm. So the bubble chart shown in this slide is the matrix size is shown on x-axis, as you can see, and then the larger bubbles mean denser matrices. And as you can see, when matrices get larger or denser, we always observe that BOTs achieves the lowest pre-processing time by far. So we wanted to also do a scalability study here. Please note that in my slide, I zoomed in. In the paper, we have a kind of more complete version of this figure if you want to take a look. So as mentioned earlier, the very slow pre-processing step in prior work makes the cost of reordering unjustifiable, even when performed as a one-time operation. And now we see that BOTs changes this situation. So let me also show you the impact of using our decision tree model, the figure in this slide. shows the execution time for selected matrices. Again, there are more data in the paper. In the validation set, normalized to the best performing K. The K value predicted by our model is indicated with a star on top, a red star on top, which, as you see in most cases, is the optimal K. So the figure shows the impact of the cluster size selection. For instance, for the leftmost workload, we see a 9 times the speed up when using the optimal size versus the worst case. So the impact is on performance. Of course, there's no impact on the functionality. And then our model achieves like 88 times time accuracy. But again, this accuracy has nothing to do with the functionality or inaccurate computation. It's just how much performance we can achieve. So next, the last numbers that I want to show you about this work before I move on to another work quickly is, so let's take a look at the memory traffic, because remember that first thing first, we want to have devotees to optimize memory traffic. That was our main motivation. So the bar chart in this slide shows the off-chip memory traffic normalized to the compulsory traffic, which refers to the traffic that all the designs would incur with unbounded on-chip memory. So if you have like a huge on-chip memory, what that would be, equivalent to basically reading the input matrices and writing the output matrices. So each bar, as you can see in this chart, is divided into 3 components. Normalized traffic for reading matrix A, I guess in green, B in red, and C in yellow. So as promised, the bottom line is that devotees mainly reduces the traffic to read rows of matrix B. That was what we were optimizing for, although we are reordering matrix A. The goal is reducing traffic for B. And then you can again refer to our paper for the for extended like analysis. And since off-chip memory accesses directly impact the total data movement, again, I want to emphasize the data movement and also the accesses to the memory, both of which are a big contributor to the energy efficiency, and even small improvement here make a big difference in energy efficiency. That's super important. And in our paper, you may also find more results on memory traffic reduction for gamma and for trapezoid. So I may not have time to go over the other example, but the other part of this part that's the core core thing that I wanted to talk about is how we can enable intelligent reconfiguration accelerators and connect it with like making decisions. So far I talked about just like perhaps accelerators, how we can run them more efficiently, how we can change something in GPU. But the reality is that we cannot keep adding new hardware based on different software and different requirements that we see in software, because it is costly, development is super slow, and in general, it's not a scalable solution. So what we want to enable, another basically directional research that we want to enable, is a unified software and hardware system. I don't want to call it a unified co-design, but basically it's a holistic view to hardware and software, in which as something in software changes, whether it's a new generation of an algorithm, whether it's a new pattern of sparsity, we can change and reconfigure the hardware with that. So, of course, why it is relevant to the topic that I wanted to discuss next. One, there are so many different aspects for enabling intelligent reconfigurable accelerators, but one is that how to make decisions based on diverse sparsity. And then for that, I wanted to talk a little bit about MISM using machine learning. As I said, basically the spectral clustering and decision tree was also about this. But now here we want to see what machine learning methods we can use to select the configuration based on the features of data. This is another work led by my second year PhD student, Sanjali Yadav, and another work published at Micro. So I don't want, I already showed you different data flows, variations of the sparsity. I don't want to go over them again, but basically, um, the problem is that um, so sparsity occurs in all of these domains, and then there is no mechanism to select what is the best hardware if either based on a domain or based on like a specific pattern within a domain. So we know that several sparse accelerators exist that use just one of the, so in very particular way, among the sparse accelerators that exist today, they use one of the three data flows that I showed you in the for when I was talking about quoties for accelerating basically the different matrix multiplication. So more recently, we have seen accelerators that support multiple data flows so that they can cover a wider sparsity range to optimize for more varied workloads. However, these accelerators still face challenges. For example, Trapezoid introduces novel data flows that cover the sparsity range. However, it does not have a method to select the optimal data flow. And then there is another work, Flexagon, which on the other hand uses an offline profiling approach, which may not be generalizable to other accelerators that support multiple data flows and require a selection mechanism. Therefore, the first challenge we target here in MISM is the lack of a fast and accurate and generalizable data flow selection method. So, but the challenge doesn't stop there. To efficiently handle diverse sparsity, accelerators typically also mix different kind of hardware component into the same fabric, not using reconfigurability. But this is not efficient either. Um, Covering the whole sparsity range means paying for like more compute units, complex distribution network, and more on-chip storage, which basically increases the area overhead that often leaves like parts like unused. So I must acknowledge that systems such as like Trapezoid improve reuse, but some components are still idle. So perhaps if you're familiar with FPGAs, you are thinking that why not using FPGAs? You are right. FPGAs have emerged as a popular solution for accelerating sparse computations, as we also see in many papers recently. But FPGAs offer a fine-grained like parallelism, and their reconfiguration fabric enables custom data paths and memory systems. But harnessing FPGA reconfigurability to create generalizable sparsity-aware accelerator remains a largely untapped opportunity. So we usually use FPGAs for like prototyping new ideas instead of ASIC, but we are not basically taking advantage of um, actual reconfigurability of the FPGAs. So to solve these challenges, this paper proposes MISM, which makes three main contributions. First, it formulates data flow scheme selections as an ML classification problem and uses a lightweight decision tree to select optimal schemes. It develops a reconfigurable engine that evaluates whether switching data flow scheme is beneficial based on the runtime matrix or not, a similar contribution to Boaties. And third, it introduces a set of FPGA-based data flow implementations that demonstrates the functionality of MISM's data flow scheme selection and basically reconfiguration engine. So let's take a look at the overview of MISM. I may not be able to get into details of that, but I mean, let's see what we have in MISM. So on the host side, we analyze the sparse matrices and extract the features from matrices, and we also create a computation basically schedule of how data points are mapped to each HBM channel because the FPGA board that we have uses HBM. The features are then sent to a decision tree, which decides the optimal decision for a given like workload based on its sparsity like pattern. And after the optimal design is predicted, we have a reconfiguration engine that does a cost analysis of whether it's beneficial to reconfigure or not. And based on that, we reconfigure the FPGA, or we may keep the same bit stream as before. And basically, on the other hand, of course, to run the new or previous bit stream, we set data based on the schedule that we have. So because I wanted to mainly talk about like how to make decisions, so we are using like data decision tree model, as I mentioned, but basically I wanted to first like motivate that a little bit. So some of you might ask, because that's a valid question, that why do we need to even use an ML model for this? So to answer that question, we run experiments of running matrices from different application domains. Again, we are targeting diverse sparsity with different data flow designs in MySem, and we observe that no one design works well across all matrices. In fact, some matrices from even same application, as you can see on the x-axis, from the same application domain need different designs to get the most optimal performance. And we realize that decision-making process is not as straightforward. So ML machine learning methods can help, but we do want to keep it simple. So our main basically objective with the data flow selection model was to keep it lightweight so that it doesn't take up storage on the host side. And we want the inference to have minimal overhead, the accuracy to be high, and the solution to be like easily like generalizable so that you can actually simply use it for like different sparsity patterns. And so to any accelerator that support multiple like data flow selections can basically use that. So to achieve all of these with a simple method, MySem uses a decision tree method. We have tried like other methods. Reinforcement learning can be helpful here, slightly more storage overhead, but if you want to super optimize it, we go with a decision tree model. So maybe I can just briefly go over like the other steps that we have in MySem, which are not relevant to how we make decisions. So we have a reconfigurable engine that basically based on taking a look at the costs of the reconfiguration itself, because the configuration itself is costly. You cannot just keep making decisions that, okay, change the bit stream, change the bit stream. So that basically evaluates the impact of changing the reconfiguration given the overheads and makes a final decision. And of course, we have, as I mentioned, we have designed different data flows for a particular FPGA. We have optimized them. This part was manual. And then if you want to learn about this different the data flows that we have and how exactly they work, this is a very dense figure, but I wanted to show you and encourage you to go ahead and please take a look at that. But the bottom line is that, so we trained the decision tree model on our FPGA-based data flow scheme for different sparsity ranges. In order to do so, we created a data set consisting of matrices with varying sparsity to capture all the like diverse sparsity that we have. So our model is lightweight because of pruning feature sets. We are not including like all the features. I didn't want to go over that because for BOTs, I already mentioned what we mean by feature sets. It is fast. Also, because it is lightweight, it achieves 90% accuracy. Again, accuracy here is not about functionality. It is all about these speedups that is being translated to. And finally, again, because of the model being simple, it is generalizable because different architectural setups can be simply retrained into the model. I want to just show two results here as the selected results. So we ran validation experiments by mapping the residual difference between the predicted and actual latency values. We observed our two value of 0.97, and most of the residual differences is clustered around 0. As you may know, R2 is a statistical measure that represent goodness of fit for a regression model. So basically, in short, we see that basically our prediction works well. And then another main result that I want to show, because I said that we have a reconfiguration in gene that chooses whether we have to reconfigure or not. So as you can see in the cases, so for instance, when we have like, if you look at like this case, so the star shows the method that MindSim selects because the overhead of reconfiguration is huge. And then if you reconfigure, you are not going to see any benefit. So if you compare this yellow one with this yellow one, basically you are going to see slow down. But putting everything together, we achieve. So this is the numbers that Barry was showing. So if you put everything together, MySim shows achieves a 2.74 times speed up. So you can find more results on energy efficiency and then like end-to-end performance comparison as well. To show basically how machine learning based decision making, very simple methods of machine learning can help in enabling intelligent reconfigurable computing. I don't think I can go over the like last piece, which is another example of making decisions, but feel free to take a look at our last year's macro paper as well, that led by my third year PhD student, Ubad Bakhtiar. And then with that, I want to conclude my talk. If you please feel free to get updates on our team work at our webpage, castle@umd.edu.cs, as well as we usually post our updates on LinkedIn. So feel free to take a look. Let me know if you have any questions. Sorry, but it took like 1 hour, but yeah, I would be more than happy to take questions. Thank you.
Okay, thank you, Bahar. So, very informative talk. Yeah, and I learned, and I actually have some questions, but first, so any questions from the audience? So you can either unmute yourself or input a question in the chat box. I think maybe I can take the first question. So, at the first part of your work, so in how to design the sparsity format, so you mentioned that for your proposed format, so it is kind of works well for the 30 to 70% sparsity, right? So I was
Yeah.
wondering, so why? So is there any kind of the principal guidelines? So for given sparsity ratio, so what is kind of the suitable kind of bullet points we need to follow to design the sparse encoding format?
That's a great question. So if I understand the question correctly, so why we choose like 30 to 78%, or why we are achieving like speed up? Because I want to like emphasize that. So if you want to get into like a wider range, of course, the accuracy won't be preserved if you don't use basically this like unstructured pruning, but then it is connected to the storage overhead. So then you won't use like the other formats because of that. I mean, even if like accuracy is preserved, but then now the question is that if you use these other formats, it might be kind of faster. I'm not sure if you have like numbers for them, but basically your storage overhead is huge. So you want, so it is basically a trade-off connecting
Mhm.
like three, like accuracy, compression ratio, and the speed. Yes, if you look at just the speed, I don't have the numbers. I cannot even say that, okay, so speed would be like better or not, but you won't even select to go with like those formats because I mean their other like aspects are not good. But what was the second part of your question? So about like the any like guidelines or
Some kind of principle kind of
mm,
guideline that because right now many papers actually they design like the sparsity format in a kind of the heuristic way, right? So we just find the kind of bright idea and so on. So I was wondering whether we can like to form kind of the methodology to guide the community to form kind of.
Yeah. No, that's a great question. My short answer is no. No, we are also got into this, I mean, in a heuristic way, but connecting this work to our other work in our lab, we are also thinking about the fact that, okay, so what if we don't want to like basically in a heuristic way get into like this format? But no, I don't have an answer for that, but that's something that we are like exploring and think about it. So still there are some parts in our work that is heuristic based, but yeah, that's a great research
Yeah,
question.
yeah,
Yes.
because you are expert, especially in exploring the sparsity. You've done a lot of the work on that. I think you have kind of a lot of the experience, right?
Yes.
Yeah, so I think that I'm not sure whether, for example, this kind of very rough idea, maybe you can like to kind of distill your experience to a machine learning model, like
The,
to
yeah, yeah.
prove that, right?
No, I actually, so one work that is ongoing is that, so on MySem, one thing that we are expanding like MySem to is that, so to be honest, MySem is the simplest kind of data flow selection method based on decision tree, but the reinforcement learning based model is basically taking into account the like a compression format as well. But actually, we are a bit more careful about compression format, although we use it for LLMs. But you don't want to, you can't always say that, okay, I want to change my compression format because there are also some additional overheads there. But yes, we are integrating that into like the RL based version of this work. And then, yeah, whenever data is ready, I would be happy to share those with you. But then there would be a compression format, co-design with data flow selection that both of them together needs to be integrated into this workflow. Yeah.
Thank you. And actually, I have another question just about this the myself. So here, so your underlying hardware fabrics at PJ, right? So I know that. So in this work, so it's mainly focused on those that how to select, do kind of good predictions, analysis, and so on. So I was wondering that. So because for the reconfigurable hardware, so we also need to consider about the hardware support, right? So I was wondering, so for this kind of the reconfigurable sparse accelerators, so do you think so? What is kind of the suitable kind of hardware support, like so, like for example, whether we consider like the CGRA and at that level, at the more kind of the hardware component level. So whether we need to also do some kind of the corresponding changes to make it more suitable for the sparsity and so on. Yeah.
Yeah, that's another like great question. So yes, I mean when we are talking about the configurable computing, how to make a decision is just one aspect that I talked about, but I mean the other aspects is that at what granularity to make this to kind of reconfigure. So again, like manually and heuristically, we have been taking a look at like this different kind of implementation of of on FPGA and kind of I don't know if this is a representative like figure or not, but I mean see if we can define these configurations that at coarse grain are separable, so that for instance we can kind of enable partial reconfiguration of the FPGAs and then like keep the connectivities and just kind of reconfigure like half of it so that we also break the this overheads that I shown in this slide, for instance. But again, so we have realized that it is a lot of like manual like effort. That is another kind of piece of ongoing like research that we are doing. So here we just realized that I mean the simplest way is to reconfigure the entire FPGA. But yes, it is again another student of mine is exploring like CGRAs. Um, but based on what we have seen, the simplest way is that all those three data, if you focus only on the three data flows, yes, there are opportunities that are obvious even by a human in the loop that okay, so this is like the very similar in all the like data flows, so you can keep it. But again, there are all of these like mix of like heuristic, human in the loop, and then making sure that how we can translate them into intelligent kind of manner. And then so we are also studying that. But the very simplest way that I can say that at least for MySim, we know that it is possible to kind of separate the two parts and enable like some coarse grain reconfiguration, but MySim itself is not doing that. It's kind of basically perhaps the next work that we are doing. Yeah.
Okay, thank
Very,
you.
very great, great questions. Yeah, these are
Thank
exactly the things that I mean needs to be done next. Yes.
thank you. And before I ask a further question, so any questions from the audience? Okay, so maybe I ask the last question. Yeah.
Sure,
Uh,
please.
so another question is about at another stack of the techniques. So about the compiler. So
Mm-hmm.
we know that in the art community, so we actually there's a lot of the kind of the sparse or the mixed sparse dance accelerators and so on. So and you work on that a lot on that. So I was wondering, so from the perspective of the hardware architecture, so do you think that right now what is missing in the software support, like especially in the compiler? So we know that is kind of pretty challenging task, right? So so in your vision, so what do you think what is the next step? So
Yeah, basically you spoiled my answer. So yes, I mean I do believe that um compiler side is like missing. And then for instance in our work, we usually so some of the kind of techniques using machine learning at abstract level is deployable at different stages. It could be deployed in at compiler level. It could be deployed as a guidelines for kind of selecting like different configurations. But definitely there is a huge opportunity to not just integrating machine learning methods into compiler, but in general, basically thinking that what else can be optimized at compiler level. That is something that we are not focusing on because we are not experts in compilers, but that's definitely kind of a missing thing. But I mean, I want to kind of also just mention that uh, because you also mentioned CGRAs, we have realized that, of course, I mean, resource underutilization is a challenge in
yeah,
CGRAs. But then there is a lot of like one of my students in taking a look at kind of compilers for CGRAs and seeing that kind of the dependency graph, the data, basically data flow graph can be optimized very well for CGRAs by just using some simple methods. But just because no one has studied that, I mean, there is like room for optimizations. So yes, I mean, definitely, I know that I mean, we people have to in our community we have to focus more and more on compilers, but that's at least not hasn't been like our main focus. But it doesn't mean that it's not important. Yeah. Again, great question. Are you guys focusing on any compiler optimizations, compiler level optimization?
yes. So right now, some of our research is, I think it's kind of about the scheduling. You can view this kind of backend of the compilers, also the scheduling for the AI workload and so on. Yes, so I think it can view. So we do not explicitly mention it's a kind of compiler, but essentially it is used as the optimization part, backend optimization of the compiler. Yeah, yeah, but
Yes,
it's
yes.
still is kind of mainly for the dense, right? So because we know that Sparse is so dynamic, so uncertain. Yeah, it's kind of a lot of the challenges. So
Yeah.
I'm not sure whether so our kind of battle to deal with the sparsity is kind of endless fight or not. Yeah,
Yeah. Yeah, yeah. No, that's true. Yeah. Integration into kind of compiler tool chains is another kind of like engineering effort, and then having that optimization is another thing. But yeah, I hope to see like more work on that to kind of yeah,
okay.
make the solutions more practical.
Yeah,
Yeah.
yeah. Okay. Okay, again, so thank you so much for your presentation and for your answers. And these visions are actually very valuable to, I think, to the entire community. Okay. And
Thank you so much. Yeah, thank you so much for having me. I was so excited to give this talk and then to get connected with people
yeah, yeah,
there. And yeah, thank you so
definitely.
much. Yeah.
Yeah, yeah, I have very nice discussion with you, and also thank everyone for to attending our this semester's efficient seminar talks. And so this is our last talk this semester, and so next spring we'll continue our series, and so see you guys next spring. Okay. And Bahar says thank you so much,
Thank
and
you.
enjoy the
Yeah.
rest of the semester and happy holiday. Thank you.
You too. Yeah. Happy
Thank you.
holidays to
Thank you.
everyone. Thank
Thank you.
you.
Bye.
Bye.
Bye.